All righty. Welcome back, everybody. Who did something not related to any of your classes last week? Those of you who didn't raise your hand, you need to go home tonight and do something unrelated to your classes. All right. Welcome back. So if you remember, although I realize it was a long time ago, in a galaxy far, far away, we were talking about I/O. And we, among other things, I was introducing this idea of interfaces. Okay, now, settle down. Interfaces and how the CPU actually talks to devices. And a very common mechanism for talking to devices is what's called memory mapped I/O. And the thing to keep in mind is, what does that really mean? That means that some device, here I'm showing a screen, has physical addresses that it represents that basically if you read and write those physical addresses, you cause something to happen on the display. Because they're physical addresses, usually in most hardware you can actually map them with the page table and thereby give exclusive access to a user of some device. So that's one of many positive things of memory mapping. So the hardware maps control registers, display memory, etc., to physical address space. What's interesting, in the old days, back when my mustache was not white, you actually had to be really careful about collisions. If you put two devices in and they shared the same physical address, bad things happened. Okay, most buses these days automatically detect collisions and prevent that, but some legacy devices you still have to set jumpers. So for instance, simply writing to these physical addresses like display memory here would put up dots on the screen in many cases. Or writing, there might be a graphics command queue, which again, it's just a set of addresses, but if you write to those addresses, all of a sudden it draws triangles or something interesting on the screen. All right? And furthermore, there's typically command registers somewhere else in memory space which say go. All right? I filled up my graphics command queue with some commands. Now draw my, whatever it is. Okay? My Angry Birds Transformers game. Okay? And you can protect this with address translation because it's normally it's done at the device or at the physical address level, so you can protect it with the page tables. Are there any questions on this? Fairly simple idea. Yeah. So the question here is, when you draw the triangle, does it take up memory? So yes, it takes up somebody's memory. There's a set of addresses that I show here which represent the interface between the CPU and the device. The device probably has a whole bunch of other graphics memory and stuff that isn't directly addressable like that. So sure, it takes up memory, but whether the CPU can see that memory or not is a different question. Very device specific. Good question. Now the other thing I briefly mentioned last time, and I'll mention it again, is some processors, like x86 processors, have I/O instructions, in and out. How many people have ever heard of the in and out instructions? Okay, they make good hamburgers, right? So the, oh wait, maybe I'm confusing that with a joint that makes hamburgers. But anyway, the point is that in and out instructions can also write to some of these registers, and there's protection involved with those instructions, but that's not in general, not all processors do that. But all processors will do memory mapping. Can anybody remember, incidentally, before I get rid of this screen, there was one or two interesting bits that were in the page table entry that might impact this? Does anybody want to remember what they might have been? So the page table entry obviously had things like valid and writable and, user. There's a couple other bits. Does anybody remember? I know we're digging way back a week ago. Huh? Well, the dirty bit, that's more for caching. Oh, wait a minute. Cache, no cache, right? So there were no cache bits that basically say in the PTE, when you're writing to these pages, don't put the data in the cache. Why would that make sense for an I/O device? Yeah. Well, not only do you not want to slow down information going to the device, but if you don't tell it not to cache, you're in danger of the information never making it to the device, right? So if you set the no cache bits in the PTEs that are mapping to these things, then you know when the processor does it right, it does not get stuck in the cache, it goes directly to the device. So that's pretty important. All right. So let's talk about getting data to and from the controller. So far we've talked about, there are these memory addresses. The simple thing you could imagine is the CPU goes in a loop. And it says, write the first byte, write the second byte, write the third byte, write the fourth byte, or maybe it does words. But it's in a loop, and you're tying up one of your CPUs, or your threads, right? That's called programmed I/O. Perfectly good way to do this. But there are block devices like disks and network devices that bring in big chunks of memory at times, but disks are a great example of a block device, that you want to transfer 4K at a time or more. You don't want the processor to go in a loop just copying from the device to memory, because why waste the CPU cycles? And so there's an alternative called direct memory access, and I want to talk you through this because this is a very common use of transistors on modern processors. And the idea is rather than wasting a CPU, we're going to build a special little transfer device where we say, take this range of memory out of the disk and copy it to this range of memory in the DRAM and then go. And no CPUs are harmed in that process, and the only thing that happens is you get an interrupt later. Okay, and so this is an example of what you might want to do. So let's suppose that we have a disk hanging off this IDE disk controller. It's on a bus. And the CPU says, gee, I want to transfer some data from the disk into memory. So the first thing it does is it tells the device driver is told, okay, by the operating system, do it. The device driver talks to the interrupt controller and basically says, start the transfer. The disk controller now gets pulled by the DMA controller. Read byte, read byte, read byte. That data then goes directly to memory. Okay, and there's no processor involved in this, and so it's much faster. So it's direct memory access. Means basically I set up the DMA controller to do the work, and later I get an interrupt saying, oh, all right, we're done. And the processor didn't have to get involved. And this is extremely helpful. It saves time, it saves power. It's overall a good optimization that a lot of processors provide. All right, questions? So now when you're asked about direct memory access in a party, you'll know what it is. And it's not because you're not remembering anything anymore. Okay. So let's talk about that notification. So how does the OS find out when something's done and it needs to be notified? Somebody want to give me some options? What? Interrupt. That's one we talked about probably, I think maybe on the first lecture, right? What else? Polling. Good. So there are at least two pretty standard options. One is interrupting, and this you know well. The interrupts go through the interrupt controller, and the device gets an interrupt whenever it needs service, and an interrupt handler is run. The other is polling, where the CPU now, again, is checking every now and then. Is it done yet? Is it done yet? Is it done yet? That's polling. And these have their advantages. So the good thing about polling is it's very low overhead. Why do I say that? I say that because the thing that's running, say the OS or the user program, checks every now and then, are you ready? And then goes back to what it was doing, and there's no interrupt, there's no context switching, nothing. Okay, so that polling operation is very low overhead. The problem is you may poll a lot and not get any results back. So if you've got a device that's very unpredictable in its timing, then polling is actually going to waste a bunch of time for you. So the trade-offs there, and the overhead of I/O interrupts means you got to save and restore registers. You're running an interrupt handler, but you don't have to waste time for finding out the device is not ready. Actual devices combine both of them. Here's a great example. So network devices. Anybody know what the standard speeds for Ethernet are today? You plug your computer into the wall? Yeah. Okay, 10. Yeah, 10 might be a good one. 10 gigabits per second, or gigabits per second. You could, gigabit networks are very common, 1 gigabit, 10 gigabit, there's 100. And so the interesting thing about that is if packets are bursting along at that high speed and you get an interrupt on every packet, a lot of processors can't even keep up with that rate. Okay? But you don't want to be polling all the time because you might miss something important. And so what actually happens in modern network cards and device drivers is the interrupt happens when the first packet comes in. You go into the device driver. It pulls out as much as it can by polling for a little while. And then when the input queues and the hardware are actually done, it returns from interrupt. And so this is a way to not have one interrupt per packet, but one interrupt per burst. And that can make a huge difference in overall performance. All right? Good. And the mechanisms have been in Linux to do this sort of one interrupt per burst for a decade now because it's so important. And we've been going into that continuous increase in network bandwidth, for instance. So now let's go back to the device driver. So the device driver, which is that custom piece of software per device that tries to provide above some standardized interfaces to the kernel and below some customized interfaces to the device. So there's a standard, every operating system defines a standard interface that the device driver plugs into so that the same kernel I/O subsystem can basically access the same devices, whether they're disk or USB or pick your favorite device. Those interfaces from above, from the top part of the kernel, are all standardized. From the bottom, of course, it's different to talk to the USB bus or to talk to an IDE disk or to talk to a SATA disk or to talk to all these different things. There are different protocols underneath, but the standardization basically helps us above. And there's typically special device configuration supported through the ioctl system calls, or ioctl, some people like to say. Device drivers are typically divided into two pieces, the top and the bottom half. Okay, so the top half of the device driver is basically the call path from the system calls. We showed you this probably lecture 4 or something. I'm just reminding you. So that top half has a standard set of cross-device calls like open, close, read, write, ioctl. This is the kernel's interface to the device driver. And the top half, if you remember, starts the process. So when a user process does a read, it goes into the device driver ultimately. If it's not in the file system already, it goes down to the device driver. The device driver starts the process and then maybe puts the process to sleep. So it starts the read. And then the bottom half comes in as an interrupt handler, and that gets the input, maybe does a DMA. And then when it's done, it may wake up sleeping threads, which are sleeping in the top half. Okay? And those threads then would return to their user process with the data. Okay? This part of a kernel, the device driver, unfortunately, is the most unstable part of any kernel. Okay, the device drivers, when things crash, it's usually the device drivers. Okay, and why is that? Well, because the kernel itself is under control of some developers, hopefully, that know what they're doing. The device driver is under control of a gazillion third-party developers who aren't always very careful with their device drivers. And there have been many projects over the years that have tried to put the equivalent of sort of virtual machine containers around device drivers to keep them stable, or even if they crash, they don't screw up the rest of the machine. Those have been of limited success over the years. They haven't caught on as much as you might like. But just so you know, the device drivers are the most unstable part of most modern operating systems. Questions? Yes? You know, the funny thing about operating systems is they've reached that stage of legacy development where nobody wants to change anything, very conservative. And some of these things are great ideas. I mean, there have been projects out of Microsoft and so on over the years where, you know, it's like, well, let's protect these interfaces. You know, even microkernels, which we'll talk about a little bit later in the term, were an attempt at encapsulating things, and they just haven't caught on. They're not always a big performance hit, but if there's even a little one, then people say, well, it's not worth my trouble. Or, oh, I got to learn new interfaces, and I'm a device driver developer that's under really high stress, and therefore it never gets done. It's kind of unfortunate, but maybe you guys can change the world, and we can start getting more agile development of operating systems. That would be wonderful. Okay. So you might probably recognize this picture, but I'm going to show it to you again. The user program says, I'm going to read something. Okay, and so then what happens? It goes into the kernel I/O subsystem. Is it in the file system? No. It goes down to the top of the device driver, potentially issues the commands and puts you to sleep. So the user program might be sleeping when you issue the commands to the device hardware. The device driver down here takes care of the device. Eventually, you get an interrupt from the device. It copies things using DMA, let's say, back to the top more normal part of the kernel, and then we wake up the process, and then we kind of transfer the data back up to the user program, and we're good to go. So that's a pretty standard path through the device driver, and you can see where the top and the bottom half of the device driver are kind of living right here. Okay, so bottom half runs at interrupt level, top half, you could think of that as running even at the kernel thread level, if you now keep a mental model of what we've been doing this term. Okay, and therefore you can put things to sleep at the kernel thread level. Questions? Yeah. This guy? This is basically asking, when the user makes a read system call, oftentimes the read system call could be satisfied immediately by the kernel because it's in the file system or the buffer cache. We'll talk a lot about these things in a week or so, actually next week. So what that's saying is, can the kernel already satisfy your request? If so, you just immediately satisfy it, and you don't even bother with the device drivers because you don't have to talk to the disk. It's already in the cache of the kernel. Good question. Any other questions? Okay, good. So let's talk about some performance concepts. We're gonna talk about some real devices today and talk about some performance. So one of the metrics that we care a lot about with devices tends to be response time or latency. That's how long does it take. Another is bandwidth. You know, how many operations can I get per unit time? These two things are not the same. Okay? This is a Sesame Street slide, right? Because you can improve response time, but maybe impact or vice versa. Now, oftentimes, making response time faster will let you do more operations per unit time, but it's not always the case. And so these are two separate measurements. The other is overhead. So there's a lot of overhead in things, but from the time I decide I want something until it actually starts happening, there's that overhead piece. And that could be any number of things. It could be the startup of the device driver or the controller. It could be queuing time, which is going to be a topic toward the end of the lecture. It could be basic copying the data to another buffer to go on. All of these things are overhead that aren't necessarily getting the actual access to happen. So most I/O operations end up being roughly linear simply because, after you get over the offset of the overhead, then basically however many bytes you're transferring, you divide by the rate at which things can go, and this particular model works pretty well under a lot of circumstances. Okay, and it works well enough that, for instance, let's take a very simple example. We got a network. I'm calling it fast, but now this is kind of blasé, right? A gigabit per second. Startup cost a millisecond. We could draw a graph like this, which basically has the size of the packet on the x-axis, and then I have two y-axes, so blue is latency and red is bandwidth. And here's that linear transfer time. That's an easy one, right? That's just overhead plus b over transfer time. This red one is a little more interesting. Okay, so by the way, latency, that's this blue one, I should have made a blue text, is S plus B over B. The bandwidth is a little more interesting because the bandwidth, there's the raw bandwidth of this network, which is a gigabit, but that's not the bandwidth you get, right? When you figure overhead into the picture, you get something much more complicated. You get the, byte B divided by how long it takes to transmit it, so the size of the packet over how long it takes to transmit it, is this red curve. And if you notice, this is asymptoting out, but it hasn't reached 125 megabytes per second, which is what a 1 gig link is. Okay, so you see that I would have to actually transfer much larger packet sizes. This is 500 kilobytes there on the far right, before I could even get to my 125 megabytes per second. Okay, so it's amazing how overhead blows the bandwidth. Okay, and so clearly when you're designing a system, keeping your overhead low is going to be really important if you're interested in getting the best out of your system. And by the way, 500 kilobytes is starting to get on the not small, right? That's not a small packet. In fact, you're going to break this up, and this overhead is, basically time to get into the kernel and stuff. But here's another thing we can talk about, which is useful. What's the half power bandwidth? Okay, now we're sounding like EE. But what it means here is that's the time at which, the packet size at which, my bandwidth in red is actually half of my available bandwidth. And if you look here, that's where this dotted line is. It's kind of at this point, which is, by the way, 125 kilobytes, I am now about halfway to the 125. Okay? All right. It's 65, so that's a little bit early, but you get the idea. All right. Here's another interesting thing. If we're talking about a disk where the startup time is milliseconds, let's use 10 milliseconds for our overhead. Look at this. This is pretty bad. So our latency has this huge 10 millisecond startup, and if you look at the half power point, it's 1.25 gigabytes. So with the disk, we're not going to get to that gigabit per second with the disk overhead until we get way out on the right, far beyond the screen. Okay? So, overhead matters. Are there any questions? All right. So does this surprise anybody? I mean, it's hard to believe how much impact there can be, even a small amount of overhead, until you actually just plot it out. And it's like, whoa, my bandwidth went away. This is why, by the way, when you think you've bought a lot of network performance, big routers and whatever, and you think you should be getting a lot more performance, you're probably losing it to overhead. All right? That's probably where it's going. And so this is why people tend to over-provision quite a bit to sort of try to make out for the overhead. Okay. So what determines the peak bandwidth for I/O? The peak bandwidth now. What do we call peak bandwidth? Well, in this case, 1 gigabit is our peak bandwidth, but we're, of course, not getting peak bandwidth. But things like bus speed can matter, okay? And so then you look at, what's things like PCIX is a gigabyte per second, SCSI can be 40 megabytes. Some of the new USB standards are getting up in the gigabits per second. This is your guaranteed not to exceed number that you can't get higher than that, but then the overhead comes into play. And obviously, the bus hopefully isn't the thing getting in your way. You're hoping that you're maximizing the device I/O, not the bus I/O. So your bus is supposed to be completely out of the picture if it's fast enough. The device transfer bandwidth can be things like the rotational speed of the disk, or the read-write rate of NAND flash, or the signaling rate of a network link, and so on. And so pretty much your maximum speed is constrained by the slowest link in the picture. All right. Questions? Okay, good. Whatever is the bottleneck is the bottleneck. So, administrivia. Now, in case you weren't aware of it, thought I'd point it out. There's actually an exam in 2 days. This is the first term I've ever tried doing 3 midterms in the term rather than a final. It's kind of an interesting experience because you're always doing a midterm, it seems. But anyway, midterm is on Thursday. All material up to this point in the slides, mostly focused on lectures 10 to 16. Timing is at 7 to 9. I'm assuming everybody who has conflicts has already interacted with our head TA, and he's told you something about where we're doing the conflict exam. DSP students, if you haven't heard from me yet, you will very shortly. But I don't know. Are there any other questions about the midterm? Obviously, there's a lot of questions, but can't answer them until after the midterm's over. Okay. I wanted to point out, don't forget, I think some of you either didn't notice or didn't, or have forgotten, there's a bunch of interesting resources on the resource page of the website. Anybody seen, how many people have gone there at least once? Okay, so there are, I've mentioned this before, but I wanted to mention it again. There are some good books on Git and a couple of books on C. And I would say if you were to, what are your basic skill set beyond knowledge of operating systems that we assume you'll have by the end of the term, it's certainly knowing how to use Git and C. So if you're still a little fuzzy on those topics like C, some people are still maybe a little fuzzy on C, there's a couple of pretty good books up there. And I would try to get more definition in your knowledge of C. That means less fuzzy. The less fuzzy it is, the easier it is, and you don't have to worry about that part. Okay? By the way, I will be the first to say that there are aspects of C that are annoying over more modern languages, but it's pretty much the gold standard. Other than Go, which is starting to be interesting, C is pretty much the gold standard for operating systems. So we're not torturing you without a good reason by making you use C. Okay. Any questions on Administrivia? Yeah. Oh, that's a good question. So we are going to allow you to bring. We're going to allow you to bring 2 pages, both sides. So you can bring your original one. You can bring a new one. All right. Remember, handwritten, no microfiche. Okay, no magnifying glasses. Yes. So the exam is mostly the new material, but the things that you learned in the previous part should be enough in your brain that you could deal with them if they came up. So I'm not going to say it's not cumulative. I'm going to say it's focused on lectures 10 to 16. Okay, so if you forgot everything you learned from lecture 1 through 9, you'd be in trouble. Okay, but... Okay. All right, good. So let's talk about storage devices. I like devices because they're up there with some of the magic that's hard to believe people manage to make work. But disks are definitely in that category. It's large, non-volatile storage that rarely becomes corrupted. It's got a very large capacity at low cost. Block-level random access, except for shingled magnetic recording, which we'll talk briefly about later. But by and large, block size, like 4K, can be written anywhere on the disk. Okay? But random access to the disk is extraordinarily slow. So you don't want to be doing random access to a disk. You only do it under extreme duress. Okay? And you get much better performance if you read sequentially. And so when we start talking about file systems next week, we're going to talk a lot about how to avoid randomness in your actual disk because it's just really slow. Okay? Flash memory is another viable technology which has gotten pretty amazing, and I have a fun device to show you guys that just came out like 2 weeks ago, but we'll get to that later. Storage that rarely becomes corrupted, that's good. Capacity at intermediate cost, 5 times disk or smaller, it keeps getting closer. It's got block-level random access, that's not bad. Good performance for reads, not as good performance for writes. Okay? You have to erase large blocks. You can't overwrite blocks ever. I'll tell you about that. And there's a wear pattern issue. If you write flash too many times, it wears out. Okay? And so your disk that you put in there that's, I put in let's say a 50 gigabyte flash drive, what's going to happen is as you write it over and over again, it's going to become 49 gigabytes and then 48 gigabytes and then 47 gigabytes because the actual bits wear out. Okay. So, yes, question? So, what happens with multi-level flash, okay, this is an aside, this will not be on the exam. What happens with multi-level flash is the way they get a lot of bits is they can store 3 bits in one cell. And the way they do that is they have 8 voltage levels. And the problem is, as you start wearing it out, there's embedded charges. It becomes harder and harder to distinguish 8 levels. So then it becomes 4 levels, and so on. And so what they do is they do something called wear leveling, which I'll mention in a moment, which is trying to spread all of the writes over the whole disk. Yeah. Okay, so if you ever opened up a disk drive, you'd probably see something like this, which is pretty impressive. So this head here, this disk head, basically is on both sides of multiple platters. So what I'm showing you here is a 3-platter disk. Okay, and they're right one on top of each other, and that means there's 6 read-write heads. They all move together. So the amazing thing about the read-write heads is up until about a decade ago or so, there was really only one company that could even make them well, which was IBM, because they're so sophisticated. They're about the same level of sophistication as chips, very small transistor size. So it's very complicated patterning. If you look here, all of the heads move together as one. So that little arm moves with a piezoelectric motion, and it basically moves in and out together. So when you're reading something off the disk, you basically move all the heads to one place on the disk, and then you read off the particular platter you care about. I did also want to point out, by the way, that these microdrives, which are no longer really sold by anybody, were pretty cool. Back in the early 2000s, basically IBM and Hitachi started these. They were like gigabyte or half gigabyte flash-sized devices you could put in cameras, but what was inside, if you opened them up, was actually a 1-inch spinning disk. Okay, they were actually, so you'd stuff, I had several of these. I had several gigabyte ones. You put them in your camera, they work just like, I know, a camera. That's also something you guys don't know about anymore, but that was a specialized device with lenses and stuff that you could take pictures with. But anyway, you could put them in there and you could record to it, and as far as you knew, it was a 1 gigabyte flash something, but it was actually spinning storage. Yes? What was that? Yeah. This is one of the larger ones. They don't make that form factor as much anymore, but this was a standardized form factor. You could buy flash that was much smaller, or you could buy this micro drive and plug it in, and it worked. You didn't know it was a drive, which is pretty cool. Now, of course, flash has gotten so dense and so much more storage that these basically somewhere around 2006 or maybe 8, they basically just stopped making them. They weren't cost effective anymore. But there was, both IBM and Hitachi were really big into that. I did want to point out also that while we're going to get terabytes worth of drive space potentially, the IBM personal computer back in 1986 had 30 megabytes of hard disk. Okay, so and a 30 to 40 millisecond seek time. So this is ridiculously small. Yes. So this is a great question. The question was, since you've got all these heads and you're moving them together, now you didn't ask the obvious one, why do I move them together? But we'll save that question for later. Can I write simultaneously to all the different platters? Not in general. And the reason is that there's so much sophisticated DSP involved in preparing the signals and reading the signals that basically there's just enough devoted for one head at a time. Even though you're moving them all together, you can really only use one of them. But that's a good question. The other reason why do you... Yeah, go ahead. Pre-processing, pretty much. Now, the physical limitation, they're also all go as a unit, and that's, again, a commodity part thing, because if you could move them independently, it'd be much more expensive. And disk drives have been in the, unless you're extremely cheap per bit category for so long that they would never be able to make money dividing up the heads. So what about the disk? So if you were to actually look inside, we've got arms that sort of have heads on either side. Rings form what's called a track. Stacks of track are called a cylinder. So if you were to take a look from down above on the stack and you were to look at all of the tracks that were on top of each other, they call that a cylinder. So you could say that the head goes into the right cylinder and then you do your reading or writing. Okay? The disk tracks can be microns wide. The wavelength of light is very close. So you can imagine that the signals here are very hard to disambiguate well. And so that's where the processing comes into play. And there are guard regions that are separating this to make this work. Track length varies across the drive, so I want you to think about that for a second. Okay, we talked about pi on Pi Day. This is a pi thing, right? What's the outer circumference versus the inner circumference? You remember that, right? So what that says is the tracks on the outside are longer than the tracks on the inside. Everybody with me on that? Yeah. But the speed is constant. So what does that mean? That means the bits coming off the outside are coming off faster than the bits on the inside. So when you move, there's a speed advantage to putting your data on the outside tracks. Surprisingly. Okay? Now, it didn't used to be that way. It used to be that what happened was as you went to the outside tracks, the bits were less dense than the inside tracks, and they put exactly the same number of bits on the outside than on the inside. But that's clearly a waste, and so with better electronics, basically, there's more sectors on the outside than on the inside now. Today, disks are actually so big that it would take days to take all the data off of them, and so a lot of companies now, Google as an example, basically only use part of their disks for live data, and the rest of it's archival. So you put stuff on maybe the inside, but you don't assume you can get at it quickly. You basically are just reading and writing the outside of the disk most of the time. Okay? So we have definitely transitioned into an interesting world. All right. Now, shingled magnetic recording is a relatively new thing, 5 years or so, which is a way to get more data off the disk. So the one way to get more data is you make the bits closer together. Okay, and there's been a lot of tricks there. The other is you make the tracks so close together that they're on top of each other. So if you actually look here, this is what the tracks look like on a shingled magnetic recording disk, where the data is actually, the data stripes kind of partially overlap each other, and the way they get the data back is via very sophisticated DSP to figure it out. Now, can anybody tell me what's a challenge with this kind of recording and random access? What would the challenge be? What if you try to rewrite some block? Anybody guess? See, what you see here is you go along one track, then you go on another track and another, and you're slowly incrementing by half track steps or whatever. What's the issue of trying to overwrite something you wrote earlier? Oh, come on, guys. You're going to overwrite somebody else's data, right? Because you're overwriting tracks on either side. So the thing about SMR disks is they're extremely dense, but people use them for archival storage. They're not for the active random access you might have in a database or something like that. So, okay. So Seagate, they had an 8 terabyte version that came out like in 5 years ago or whatever, and Hitachi had a 10 terabyte. Those were kind of the first SMRs, and they've been around a lot, but the technology has improved so much that SMR is not a requirement for high density anymore. Still around. So, magnetic disk performance. Again, we said the cylinders are everything that looking straight down. It's a cylinder of tracks. The head goes through all the platters at once. There are some number of platters in a disk drive. How many platters are in typical disk drives these days? Anybody know? 5 and let's say we talk about a 3.5-inch server drive. Okay, is it 3? Somebody said 3. Okay, I showed you 3 from 15 years ago. Okay, we're talking 8, 9, Okay? And these things are spinning. There's so much turbulence inside these disk drives when they're spinning that they fill them with helium and other things to make it all work. So these are pretty amazing devices. Readings and writing of data is a three-stage process. You got to seek in to position the head at the right spot on the right cylinder. Then there's the latency, waiting for your sector to get to where it is, where the head is, and then the transfer time to actually write to the disk. Okay, so this is basically you start at one point in the disk, you move the head in, you wait for the rotation to happen so that you're over where you're going to read or write, and then you do the reading and writing. And those are the three components. And so if you were going to try to come up with a performance model of the disk drive, you'd have to take all three of these into account at least. Now, it turns out I'm going to tell you in a second that there's other components, but these are the basic ones. Questions? Okay. Now, so if we were to come up with a model of the disk, we'd find that disk latency has at least 5 components. People typically talk about queuing time when we talk about queuing theory in a little bit. That's the time it takes for the request to make it through the queue. Then there's the hardware controller, which is the time to get the command out to the actual disk itself. And then there's the seek plus rotate plus transfer time, which is those 3 components I just told you about. And can anybody tell me what are the things that you really need to be careful about if you're building a file system? What things might you want to try to minimize? Say it again? Certainly the queue time, but sometimes that's pretty hard to get rid of. We'll talk about that in a moment. What else? So controller time is not really under your control because it's hardware. What else? Of the seek, rotate, and transfer, which are the ones that we really want to avoid? Yeah. Seek time. Boy, I'll tell you, it's only 5 milliseconds or 4 milliseconds, but that's a lot of time. Okay? The rotational time, well, you can't do a lot about that because when you start looking, you're at some random spot. So you're on average going to have to wait a half a rotation to get to where you want. And then the transfer time is also kind of tied up in the speed of the disk and the density of the bits. And so really seek time and software queuing time are kind of the 2 knobs that the operating system has a lot of control over here. Okay. And I will say, by the way, that how do you get control over seek time? You do a good job of placing your data on the disk. Okay, so obviously data layout is going to matter a lot as well when we get into file systems. Okay, questions? Now, so here's some typical numbers. I always love updating this slide whenever I teach this class. If you look at the top there, Seagate's run-of-the-mill server, well, it just came out, but run-of-the-mill server drive, 14 terabytes, 8 platters, 3.5-inch form factor. The density of bits, if you were to look straight down on a platter, is bigger than a terabit per square inch. So you guys imagine a square inch and put a billion bits in there. That's a lot. Okay, trillion bits in there, sorry. That's a lot of bits. Okay. Average seek time is about 4 to 6 milliseconds. The interesting thing about that is you might say that 4 to 6 millisecond time is assuming you go from every track to every other track and add them all up and average. In reality, a good operating system is going to get you 25 to 33% of that number. And why is that? Because you do better layouts, you're not seeking a lot. Okay, so typical measurements that what you actually get is going to be lower than the real number, which is kind of interesting. Most laptops have somewhere between 3,600 and 7,200 RPM. 3,600 RPM is lower power, but it also takes longer for for the data you want to get under your head. 7,200 RPM is sort of the higher performance laptop or disks for laptops or desktops. You can get 15,000 RPM or 20,000 RPM drives. They sound like jet engines when you turn them on. I mean, you turn on, if you wonder why server rooms are so noisy, the server rooms with the really high-speed disks, they make a lot of noise. There's a lot of other noise in there, but that's the source as well. Okay? Questions? So 14 terabytes is a lot. Okay? Any of you out there that don't think 14 terabytes is a lot? That is a lot of Game of Thrones episodes. Okay? That's a lot. Even at highest density, or highest resolution, that's really a lot. Okay. So, question? No? So what's the assumptions of our disk performance? So if we ignore queuing and controller for now, average seek time 5 milliseconds, 7,200 RPM. Okay, here we go. How many milliseconds in a minute? 60,000. Divided by 7,200 revolutions per minute gives you about 8 milliseconds for a revolution. Okay? So the transfer rate of 50 megabytes per second and a block size of 4 kilobytes, you could figure this out. You could say, oh, look, 4,096 bytes divided by 5 times 10 to the 6 bytes per second gives me about 81.92 microseconds or 0.082 milliseconds for one sector. Okay? I'm just giving you some ideas of orders of magnitude. We're being computer astronomers right now, right? So, for instance, what if we wanted to read a block from a random place on the disk? Okay, this is a simple matter of math, right? Add it up. So 5 milliseconds seek on average. Rotational delay, 4 milliseconds. Why did I put that in instead of 8? Expected, right? Expected time is half a revolution. Okay? Transfer time is 0.082, so it takes 9.082 milliseconds. So if you were to actually figure this out, what you'd come up with is about 451 kilobytes per second of a random block from the disk. Okay? Notice that is a lot smaller than 50 megabytes. Okay? So look at how much we've dropped, how far we have fallen. Right? What if we don't actually have to move the heads? If we're on the same cylinder, well, we avoid the seek time. We have the rotational delay and transfer time. We get down to get up to 1.03 megabytes per second. Now we're getting closer. Still not 50. Now, if we read the block, the next block on the same track, this is better, right? We get basically 50. Okay? So you can see there's a huge difference if you're a file system designer between seeking a lot and not seeking. Okay, see that? That's a difference in, from 451 kilobytes a second up to 50 megabytes per second. Big deal. Okay? We'll talk a lot about that next week. So the key to using this effectively is to minimize seek and rotation delays. Questions? I know it's always annoying to see a bunch of actual numbers on a screen, but, you're all engineers. We can deal, right? So, much of the complexity that we're going to talk about in file systems that aren't designed specifically for flash is really around this. It's amazing when you start looking at file systems and you look at how complicated they are. Much of that complication is because of what I've got on this slide here. It's got to avoid the random reads to random spots on the disk. That's where you get complexity. Okay, and there's whole file systems like the log structured file system whose sole job was to try to only write consecutive things on a track and thereby get really a high write bandwidth. Sorry, I'm having trouble talking today. So that was the reason for that one. Okay, so there's lots of intelligence in a modern disk. If you were building an old version of BSD Unix back in the day, what you'd find is the disk device driver subsystem actually talked about moving to certain tracks and certain sectors. And the operating system knew where the data was on the disk. Okay? Not today. Okay? Today, the controller on the disk knows where the data is on the disk. So there's really sophisticated error correction codes. There's something called sector sparing, which the controller on the disk drive figures out what's bad and transparently maps your queries to the good sectors, so you don't even know what bad sectors anymore. There's slip sparring for remapping sectors as well. Multiple ways of doing this. Track skewing. There's many optimizations. Bottom line, we'll talk more about this next week, is when you read and write from a disk today, you're asking about logical block addresses. You're not saying, here, give me something off of, cylinder 1, disk platter 3, track, whatever. Just don't do that anymore. It's all logical block, and it's all hidden inside the controller. So there was an interesting Moore's law-like exponential growth in cost per byte, exponential decrease, I should say, in cost per byte. That was great for years and years and suddenly tailed off. It's getting really hard to make really dense disk drives. So here's an example. I pulled this one out, very recent. This is the Seagate Exos X14. This is not shingled. This is just perpendicular recording where the bits are through the media perpendicularly. 8 platters, 16 heads, helium-filled to reduce friction. It's got about a 4 millisecond average seek time. 4 kbyte physical sectors. So it used to be when you talked about a 4 kbyte block on the disk, it was a bunch of 512 byte sectors put together. Now the physical thing is actually 4K, and if you ask for the supposed 512 byte thing off of that 4K sector, that's an abstraction that the disk drive is doing for you. 7,200 RPM. It's got 60 gigabyte SATA, 12 gigabyte serial interfaces. It's got 261 megabytes per second transfer rate. It's got a 256 megabyte cache on board, and it's about $615. So this is a pretty sophisticated way to get, 14 terabytes. And it's I always like to look at technologies like this because this is sort of the amazement level. How do they possibly make this work? I mean, terabits per square inch. I mean, when you guys go home, you should draw a square or go to a party. Can I tell you about what I learned in class today? A terabit per square inch is on modern disk drives. You'll be the life of that corner of the party. So just to show you for comparison, once again, I showed you this earlier, IBM personal computer, 300 megabyte hard disk versus 14 terabyte. It had 1 platter, I didn't write that down here, 30 to 40 millisecond seek time versus 4 milliseconds. Price was about $500. It's interesting how price points are relatively constant over the years. That has something to do with marketing, But notice that here we've got like less than 0.05, less than 5 cents per gigabyte. Here we had about $17,000 per gigabyte. So your bits are cheaper now too. All right, let's take a break, and then we're going to talk about SSDs. So I had a good question here about platters. Why are there 16 heads for 8 platters? Because the platters have 2 sides. Okay, so it's it's as dense as you can possibly fit, and when you're shoving 8 platters with 16 heads into a little tiny space, that's why they have to use helium, because otherwise it would be a really serious problem. Okay, now SSDs. How many people have a laptop with a solid-state drive on it? A lot of you probably, yeah. So these have been around. So 1995, these weren't really SSDs. They were called non-volatile RAM, and typically you'd get a card that had some batteries and some DRAM on it, and you could plug it in and it would store the contents of its memory even when power got lost. But we started to get NAND flash showing up in bigger quantities, and around 2009 we started getting multi-level cells with 2 or 3-bit cells, and flash just got big. Okay, and how does flash work? Flash has a special transistor with 2 gates on it, and that transistor, if you force charge into one of the gates, then you'll get a switch that's open, and if there's no charge there, you won't, and so that's how you get a 1 or a 0. It's the presence of a charge or not on that little isolated gate. And so because these are the same size as transistors that people have been learning how to shrink, flash has been sort of riding the wave on increasingly smaller and smaller transistor sizes. Okay? What's interesting about flash is even though it's in transistor form, you still have to deal with it in big blocks. And so typically in NAND flash, there are blocks that might be 256 gigabytes or 256 megabytes. I'll show you this in just a second. But there are big chunks of memory that you have to erase, and then you get smaller blocks like 4K in size. No moving parts, so that's cool. There's no rotate. There's no seek. So what about your file system? Does it have to optimize? Not for seek, right? Because there is no seek. It's all random access. What's interesting is people put these SSDs into their existing systems. They keep the old file system. The old file system's optimizing for things it doesn't even have to care about because there are no tracks, there's no rotation, there's no seeking. And so over the last probably 5 years or more, 10 years, it's been a slow process. Operating systems are starting to recognize when you have an SSD and you're not doing as much of that optimization, which doesn't need to be there. Okay. So here's an example of the architecture. So typically there's a lot of chunks of memory, which are blocks. There's a memory controller, which controls the NAND array. And then the other thing the memory controller does is it makes sure that when you're writing that you don't write over worn-out memory. And so it's doing something called wear leveling, which is every time you go to write a block, it picks a new one for you to try to distribute all the writes over the set of blocks that are in the actual hardware. Okay, so there's no seek or rotational latency. The transfer time to transfer a 4K page can be very fast, hundreds of megabytes per second. Of course, the latency here is queuing time plus controller time plus transfer time. It's missing the rotate and seek portion, right? Highest bandwidth, sequential or random. Okay, so this sounds like maybe we could design our file systems a little differently. Writing data is a bit complex, though, okay? So, for instance, we might have 4 kilobyte pages, 256 kilobyte blocks are erased at a time, okay? And you cannot overwrite data that's been written. So what typically happens is you erase a big chunk of blocks and you save that on a free list, and then when you need new data, you write to blocks off the free list, and then when you're done with, say, this blue one, you recycle it. You wait until everybody in the block is recycled, and then you have to go through an erase process on the blocks, and so that takes time. So it's a little different than the way a disk works. Okay? The controller is doing transparent remapping under the covers again. So the way you get wear leveling to work is I'm writing block 493, I think. The operating system thinks it's writing block 493, but in fact, the controller is remapping block 493 to different spots on the chip over time. The more and more you write it, it goes to a different place. Yes?
So all of the remapping thing is based off the wear level, et cetera, on the chip.
Well, it's hard to call it a chip. It's the controller. It's in the package, right? So when we look at something like this here on the left, this is an example of an SSD replacement for a hard disk drive. So rather than that Seagate 14 terabyte drive, you might put one of these in. Might also have 14 terabytes. You put that into the same slot, and all of the electronics inside of that is the thing that's doing the wear leveling. And so I'm reading and writing an interface that I think is a disk drive, but is really this SSD, and under the covers it's actually remapping the blocks I'm writing to all over the place to try to wear level. That's right. Okay, that's right. So the SSD manufacturers have a firmware controller on there typically. Now, one thing that is new, by the way, since you brought it up, or sort of brought it up, is there is flash that you can plug directly in that looks like DRAM these days. It's starting to be a little different. This particular SSD on the left there is a direct package replacement for a spinning storage drive, and you can just plug it into your computer, and the computer will just work. Okay, modulo some interaction with that firmware. You can also plug in some of these new cards that give a more memory level interface that doesn't look like a disk drive. Okay? All right. In fact, I even saw somebody mention Optane, which is one of Intel's new products. I saw that on Piazza. Okay. So, let's see, I guess that's all I really wanted to say. All right. So here is a current 3.5-inch SSD that looks exactly like a disk drive. 2017. It's got more performance because it's actually got dual 12 gigabit interfaces. The sequential reads and writes are 860 megabytes and 920. So you notice that's at least like a factor of 4 faster than a regular disk drive. The random reads and writes, number of operations per second, are lower, but it's still not any seeking time involved. However, that 14 terabyte drive I showed you before was $600. This 15 terabyte drive is $6,000, right? So there's a little bit difference in cost. All right. This is the one I wanted to show you. This came out like a week ago. There's a company called Nimbus. It gives you a 100 terabyte drive. All right. And I have no idea what the actual price for this thing is, but people were tossing around $50K to get your 100 terabytes in a standard 3.5-inch form factor. And what's amusing about this is they spec this out as giving you unlimited writes for 5 years. That's their guarantee. Despite the fact that flash wears out. Anybody want to talk me through the economics of this? How can they guarantee unlimited writes for 5 years? Yeah. Well, you could say they stuff more than 100 terabytes in there. That might be part of it. I think the other thing that's more likely is over 5 years, you just can't write enough of it to wear out. So if it rearranges with wear leveling, they're going on you take this 12 gigabit per second interface, and it's like, how long would it take to really write the whole thing? And they're just doing that calculation. So they probably have a little spare on there too. But it's kind of funny. This is just really big. By the way, if I said 14 terabytes was a lot, 100 terabytes is even more. Okay, that's more than just Game of Thrones. You'd have to find another show. Mr. Robot. How many people ever saw the Mr. Robot series? Do you guys? That was fun. I'm waiting for the conclusion at the end of this year. But anyway, okay. So what's interesting here is if you look at the price per bit, flash has been coming down and converging with hard disk for a long time. there was a prediction that they were going to cross back in 2013. Things keep moving out a little bit, but if you look here, this is arguably very modern prices. This is about 0.4, 40 cents a gigabyte, and the big disk was 0.05, so 5 cents. So it's not quite there yet. But boy, this second one blows away anything you can get for spinach storage. I mean, yeah. That's I/O operations per second. So think of a 4K block, but randomly. Yeah. Okay. So, is a Kindle, you know what a Kindle is, right? Or are we beyond Kindles for you guys as well? Very cool reading device. You can sit in the sun rather than, I know your phones and stuff, you hide in the shade when you're watching them. But so the thing about a Kindle is it's got storage on it for books. The question might be, if you start with an empty one and you fill it with books, is it heavier? This is your amusing calculation for the day. How many people think it's heavier? Okay. Only folks that think I would not ask this question if it wasn't amusing. So, actually, yes, but not by much. So flash, as I mentioned, works by trapping electrons. You got a floating gate, and if you put electrons on there, you get 1 bit, and you get no floating electrons, you get none. So there's actually an argument that the erased state is lower energy than the written state. Applying, so now we could say, look, the original Kindle had 4 gigabytes of flash. Half of all the bits in a full Kindle are going to be in the high energy state. Why half? Well, because I'm going to assume that, if you were to average the number of ones and zeros over all of the books you got on there, you come out about half, right? The high energy state's about 10 to the minus 15 joules higher than the low energy state. That's minus 15, by the way. So, pulling out our E equals mc squared, which we can do, what we find is the full Kindle is about an attogram heavier, 10 to the minus 18th grams, than an empty one. So the answer is yes. Of course, the best scale is 10 to the minus 9 grams. So you're going to have a hard time measuring this thing. And, by the way, can anybody think, assuming this calculation's correct, what's a pretty serious thing this is missing? Yeah. No, it's okay. It's getting electrons from the battery and stuff. So, but it's the battery, right? So you'd have to actually charge the battery back up to exactly where it was before you filled it, and then you'd have to make sure that it wasn't hot because that'll add energy as well. And so it's a little dicey calculation. But of course, the weight difference is overwhelmed by the battery discharge and the weight from getting warm and all that sort of stuff. But I have the reliable source that this is correct. Back in 2011, I actually answered somebody's question in their science, whatever. You can look this up, but there you go. There's your important information for the day. By the way, we always believe that person. I mean, I know I would. So, so I wrote this very limited article. You guys you can see the calculation. You can see how by limiting exactly the question I was answering and telling what my assumptions were, you charge the battery back up, I could answer this question cleanly. You might argue, but I missed stuff. That's okay, but I was very clear. The next thing that happened was amazing. So the next thing this New York Times article got, things didn't really get retweeted back then, but it was picked up by a bunch of news agencies all over the place. And then the next thing I know, we've got people writing videos that say things like, the weight of the internet is that of a strawberry. I am not making that up. Boy, you know who comes out of the walls. That was just a bizarre year. I mean, people would forward me, well, I love your calculation. Look, here's what the internet weighs. It's a strawberry. And then they'd go on to this and that and the other thing. And it just, they had no assumptions, and I had no idea what they were actually computing. So anyway, so the summary, the pros versus hard disk drives for SSD is very low latency, high throughput, no moving parts, which leads directly to reliability. The weight is light. The power is less, although write power is still high. It's very silent, shock insensitive. You can read essentially at memory speeds, although writes are slower. Cons, smaller, although, I just showed you that's really no longer true, right? That 100 terabyte drive is big. And also there's a lot of options of combining a small SSD with a large hard disk for caching. You guys are all aware of caching, right? The block write performance is asymmetrical, so it's a little crazy, and you can only erase big blocks and keep them on a free list and then write the erased ones. You can't overwrite a block. So there's garbage collection algorithms in the firmware on those devices that are complicated. And the drive lifetime has some limit because of overwriting and wearing out, okay? But things are changing rapidly, so I thought I would point out there's a bunch of new technologies that are kind of exciting. So there's a carbon nanotube memory that may actually appear by the end of this year that looks like it has infinite write performance, so it never wears out. It's as fast as DRAM on reading and writing. It's lower energy and denser. This could be very cool. Now, there have been many very cool potential technologies I've seen in the years, so let's, get me again next year and ask me whether it came true. But I was at Hot Chips, and this company Nantero sent somebody to talk about it, and I got him to write a paper in IEEE Micro, which so it sounds really cool. Anyway, all right. So, are there any questions before we move on? So the nanotube memory. It's pretty impressive. I mean, it's very small. They think they can get 16 times the density of DRAM in many layers. So it's in 3 dimensions. It's non-volatile, so it never loses its data. It's not subject to cosmic rays, which some DRAMs are. It seems like it can handle huge amounts of heat. Imagine soon that everything will have persistent memory in it, including the walls and your sunglasses. I don't know. This could be pretty fun. Yeah, question? Well, DRAM, so the difference between DRAM and SSD is DRAM is all about capacitance. And so there's very special fab lines to produce DRAM, and they build what are called trench capacitors, where you have these really deep things that go down in 3 dimensions, and then you have a dielectric inside, and then you have another piece of metal, and that's a trench capacitor. And those little tiny capacitive things give you a 1 or a 0. And there's a certain limit on, how dense you can put them together, and then how many layers you can, you put some leveling, and then you can put multiple layers and so on. So it's reaching limits. SSD is literally a transistor with rather than a capacitor, it's a transistor with this floating gate that gets charges on it. They're superficially the same, but the SSD is non-volatile, whereas with the capacitor in a DRAM, as soon as you turn the power off, you lose all your information. So that's the biggest. I mean, that's a huge difference, is the non-volatility, because you want to keep your data around. Yeah. I don't know. I mean, this could. Let's wait and see what happens, right? I'm gonna take a wait and see attitude. I have to say I'm old enough. When I was growing up, it was very cool. It's like, oh, look at those bubble memories. That's gonna change the world. And there were these little bubbles that were moving around. You should look them up. But this one, I actually believe this one could change the world if it did what they said. But let's wait a year. Okay, ask me in a year. But if you could literally have something as fast as DRAM and put non-volatility everywhere, that would be a game changer. But think of the things we're used to now that we would no longer be able to do as operating systems people, right? Because this is an operating systems class. You can no longer reboot to fix bugs, right? If everything's always persistent all the time, there's got to be something else, some sort of reinitialize, right? And this is already an issue. I mean, I don't know. I have my iPads and my phones and stuff. Basically, you reboot it and it comes back exactly where it was. That does not always fix a bug. But I think the power of non-volatility is potentially very amazing because, now you can have little devices that just keep track of everything and for a long time. So, all right. That's my plug for something I'm not even sure I believe in yet, but I think it might come true. So let's finish up today by performance of the I/O subsystem. We'll pick this up after the exam. But metrics for an I/O subsystem are things like response time and throughput. We can talk about the effective bandwidth per op. So, for instance, the number of ops, the fixed overhead, and the time per op can tell us what the effective bandwidth is. What we know, and as we get into queuing theory, we're not going to talk about it this time because it's too late to get too into it, but queuing has this behavior that as you get closer and closer to 100% utilization, things go through the roof. And we're going to show that behavior with some simple equations next time, okay? A week from today. That means you can never run anything at 100%. Now, what's 100%? Well, that would be 100% of the throughput that this I/O device could handle, plus controller, tells me something about what am I not to exceed in my queue without this crazy nonlinear response time. All right? We got to be very careful about running that thing at 100%. So contributing factors to latency are going to be the software and the operating system, hardware controller, I/O device service time. Those are all kind of obvious things. Queuing, big deal, can lead to huge increases of latency. And what are the solutions to this? Well, we're going to have to understand it first, but increasing the number of I/O devices, reducing the overhead, there's going to be a lot of things that we can do there. And for instance, one of the things that we would love to have is a very simple world where everything's linear. So what I show here is data arrives, it goes through the queue quickly, there's some deterministic service time, all the arrivals are exactly the same amount of time. Isn't that a lovely world, right? Service rate, we can talk about 1 over the time to service, that's TS. We can talk about the arrival rate is 1 over TA. Utilization is lambda over mu. That number is in theory less than 1. If you think a little bit about this, if TS is too big and another thing arrives before the first thing's done, then the best you're going to do is just service, continuously queue forever, right? So this seems nice. This is where average is the total story, and this is this ideal world where my offered load and my delivered throughput are identical, and when I have too many things coming in, then the queuing delay starts increasing linearly and the queue just fills up indefinitely, so clearly we can't submit more stuff than we can handle. The world, unfortunately, isn't like this. The world is bursty, and we'll close with this thought, but if you look, arrivals, like here's an arrival and I'm busy processing stuff, and then during this period while it's processing, you could say the server is busy, but look, this orange thing came in while I'm still busy, and then this light blue thing came in, and now the orange thing only gets to go a little later, and the light blue thing later, and so on. And if you look, what's happening here is they arrived in a quick burst, and even though the total amount of time for all four of them is the same in the previous slide, this dark blue thing is the only happy one because the orange one and the light blue thing got stuck in the queue a long time. And this is 100% because of burstiness. And the world is bursty. All right? And we'll talk about that after the exam. So keep that thought in your brain, and also remember a Kindle gets heavier. So in conclusion, we talked about disk performance. Queuing time plus controller plus seek plus rotational plus transfer. We talked about rotational latency is on average a half a rotation, and the transfer time is basically the spec of the disk and how fast it's spinning and what the bit density is. We talked about very complicated device interactions, response time being queue plus overhead plus transfer. Talked about hard disk drives and solid state disk drives, or solid state disks. And we're going to talk about also next week how systems try to deal with this weird rotational delay. Okay. And we'll actually get to this next time where I'll tell you how to interpret that equation in the bottom. But everybody have a great exam. I'll probably be in Pimentel. But you'll watch for Piazza for where you're supposed to go. And if you feel like you don't know where you're supposed to go, make sure to ask us, because maybe your email got overtaken. All right. No lecture Thursday. You can use it to study.